to welcome Steve Gottlieb today to give what is the latest and perhaps the last. We'll have to rebrand after Steve's talk, 50th anniversary seminar series. So Steve has been a NERSC user for at least 21 years. Unfortunately, our records don't go back much farther, but I did find your name on a paper that acknowledged NERSC in 1995. So I know you've been publishing results from the center since at least that long. I have this metric, Steve, that I try to normalize across years to see who has used NERSC the most over the years.
Don't talk about that, Richard.
You're in the top 5. You're in the top 100 of our 38,000 users. You're in the of all time. You're in the top 100 for sure. And you've been on NUGEX, so we thank you for that. And Steve is going to talk to us today. Oh, Steve, I forgot your title. Distinguished Professor Emeritus and Provost Professor of Physics Emeritus at Indiana University. And Steve's going to talk today about Lattice QCD at NERSC by the MILC and the Fermilab Lattice collaborations. So with that, Steve.
Okay, I'd like to thank Richard for inviting me to give this talk and all of you for attending. I'm going to start off with an outline if this goes right. So there'll be a brief introduction to what I think this talk is about. Then I'll describe a little bit about Lattice QCD because it's related to the anniversary. There's going to be some ancient history. Then I want to talk about some physics goals and show you a few of the notable results. I have some benchmarks, which should be of interest to people that like GPUs, but maybe are not that interested in QCD, and a couple slides about GPUs. And Richard asked me to say something about our future needs. Of course, we're here to celebrate the 50th anniversary of NERSC, but I'm neither a historian nor an archivist, but I tried to recover some of my early notes and results, and I'll talk about that not immediately. That's the part that's ancient history. And of course, we don't just want to talk about the past. We want to say something about what's going on now. And I want to tell you about Lattice QCD, since not everyone is a Lattice QCD practitioner, though for a while I thought maybe only my collaborators would show up. And I also want to mention that I'm very pleased that the MILC code has been used for several generations of benchmarking for NERSC computer acquisitions. And I'm excited to see what they did with that for the next acquisition, which is coming up. So let's talk about Lattice QCD. First of all, QCD stands for quantum chromodynamics. It's a 50-plus-year-old quantum field theory of the strong interaction. The strong interaction is a theory that describes quarks, which are the matter in QCD, and gluons, which are the force carrier. So this is the analog of quantum electrodynamics, where the electrons are the matter and the force carrier is called photons. Now, in QED, the strength of the interaction is determined by the charge of the particles. In QCD, this is replaced by something called color. And that quantum number can take 3 values. Usually we call it red, green, and blue. And it's mathematically comes from the group, this special unitary group of 3x3 complex matrices. Now, the strong force is very strong. So there's this concept of quark confinement, and you have the matter bound into states called mesons, which are made out of a quark and antiquark, or baryons, which are made out of 3 quarks. There are some exotic states, but I'm not going to get into that today. So the bound states have no color. They're color neutral objects. They don't carry a bare red, green, or blue, because there's red and anti-red, green and anti-green. And they make, they're bound together, so they have no net color. And then the nuclear force is a residual force of the neutral objects, protons and neutrons, for instance. And this residual force is like Debye force or van der Waals force, where induced dipole moments, leave a weak relatively weak force. But of course, the strong force is so strong, the nuclear force is strong, but not as strong as the confinement force. Now, most of our mass comes from these interactions, the gluonic interactions, not from the Higgs. So you always hear these talks about how Higgs is the origin of mass. Well, our mass comes from the gluons, and the quarks, which get their bare masses from the Higgs, they're very light. So Ken Wilson developed lattice QCD to go beyond perturbation theory. And so the continuum of space-time is replaced by a four-dimensional grid of discrete points. The quarks are described by complex fields at each of the grid points. And they're either 3 complex numbers or 3 times 4 complex numbers, depending upon which formulation you use. And the gluons, again, they're like the photons. Instead of being 1 complex number, they're a 3 by 3 complex unitary matrix. So that's something about lattice QCD. And then what do we do with this formulation? Well, basically, we're doing what's like a Feynman path integral. But instead of having e to the I times the Hamiltonian, or e to the I times the action, we change this to a Euclideanized theory, and then we get e to the minus I times e to the minus the action, and it becomes more like a statistical mechanical problem, like the partition function, than a standard quantum mechanical path integral. Well, that helps us a lot, excuse me, in terms of numerical stability but it limits what we can calculate. So some of the methods we use are what are called Monte Carlo methods. We do a lot of sparse matrix solves, and the basic algorithm for generating new gauge configurations is like a molecular dynamics in a new simulation time that is not the ordinary time that we know and love. And so the first step of the lattice calculations are to create an ensemble of gauge fields. And we have an ensemble. These are the properly weighted paths in the path integral. And so we tend to generate at least 1,000 of those in modern calculations. And then we take averages over these gauge fields in the ensemble of any physical quantity we'd like to calculate of quarks interacting with these gauge fields. And of course, larger ensembles give better averages over the quantum fluctuations. But how do you create an ensemble? Well, you have to start off by selecting several physical parameters, and these are color-coded. So in red, we have the lattice spacing, so the distance between these grid points in space-time. And this is equivalently described by the gauge coupling, which we usually denote by beta, which is 6 over g squared, where g is more like the electron charge, but for the strong interaction. So actually, in our code, we set beta, and we find out what the lattice spacing is after we've done the physics. And then we have to have a finite physical volume to put this on the computer. So there's a grid size, which is usually n space cubed by nt for the time direction. And then in green, we have to set up the quark masses. These are called the C quark masses, which are the dynamical quarks that affect the interactions. And so usually we set the lightest quark mass up and down to be equal. So that's denoted MUD here. And then there's the strange quark, and the fourth quark that we deal with is the charm quark in current calculations. And as I say, sometimes we split MU and MD, but not that often because they're very close together and much lighter than the strange and charm quarks. And then each of these parameters that we set results in some systematic errors, and we have to control the systematic errors. So in red, again, is the lattice spacing. We need to take the limit of the lattice spacing goes to 0, just like if you're integrating a differential equation with a numerical method and you're taking a time step, you need to find out what happens when that time step goes to 0. And then we have to take the infinite volume limit, or at least a big enough volume so we don't think it's significantly contributing to the errors. And finally, we have to tune the C-quark masses to reproduce the known masses of certain particles. And then we have a good simulation on that lattice spacing, and then we go to the next lattice spacing. So one question is, why do we use so much time? Well, each thing we do to control the errors better involves more time. So for instance, if we have the lattice spacing and don't change the volume, it takes about 2 to the 6 times as much time. And 2 to the 4th of that comes because if you have the lattice spacing and don't change the volume, that's 2 to the 4th because it's a space-time grid. And then other things you have to adjust, like time steps and iterative solvers may take another factor of 4. So this is a rough estimate. If you just want to double the linear size of the system and not change the lattice spacing, that's just a factor of 2 to the 4th. And if we want to make the quarks, adjust the quark mass so that they're lighter, for instance, that makes it harder for the iterative solvers. So for many years, it was actually too expensive to bring the up and down quarks down to their physical value. But in the way we're doing physics now and with the power of the computers we have now, that's not a problem anymore. Okay, so in addition to just creating the ensembles, we have to do a variety of what we call measurements on the ensembles with what are called valence quarks. And a lot of that time goes into the iterative solvers again, particularly for the light quarks. But one difference between doing the so-called measurements and creating the ensemble is once you have the ensemble, it's on tape. You can bring it on and off it, to disk as you want, and you can actually run lots of stored configurations simultaneously. And in some places we bundle and do, 10, 20, 30 configurations in one job to help the managers feel big that we're using a large number of nodes at a time. So generating configurations requires high speed, ideally, so that you don't spend a long time generating the ensemble, and we'll talk about that a bit later. But the actual measurements, once you have the ensemble, is more like a capacity problem, but it's a capacity problem at a certain level of capability. So this is a picture or depiction of some of our ensembles, not by any means all of them. And the size of the circle in terms of the area is reflective of how many configurations we have. And the x-axis is the lattice spacing. It's actually lattice spacing squared. So we'd like to go to the lattice spacing going to 0, which is on the left-hand side, closer and closer to the left-hand axis. And there are 3 or so different light quark masses that we've used here. And the ones at the bottom are the ones closest to the physical value of the light quarks. And we have quite a number of other ensembles. And the ones at the bottom, you notice, are big because that's where we need the best statistics. And so the big circle, red circle to the right, corresponds to 10,000 configurations. And most of the other ones at higher mass are capped at 1,000. And then there's a purple one on the lower left. And that one, we're going to see more about that in a couple slides. So remember, this is about some history. So here's the ancient history. In the beginning, so I checked my disk and I tried to find the earliest references I could to computing at NERSC. Many times I've switched from computer to computer, so it's a lot of fun trying to find the right area from before. But I was able to find something. April 28th, 1995, there's an email from my longtime collaborator, Bob Sugar, who was the original member of MILC and really kind of the head of our collaboration. And what Bob said was, I just spoke to Greg Tomashke, who is now running the NERSC T3D. One or more of the paying users has complained that we are interfering with their work. the upshot is that we are essentially going to be running on background until our proposal is approved, which should be soon. Well, I couldn't actually find a copy of the proposal, but I found another email from Bob less than a month later. It was an email to Bob, and I was CC'd. And what it says is UC has about 16% of the machine under the current operating mode. We're trying not to give any single user more than 3% of the 16%. Your request is, and actually Zoom is covering up some of what I want. Let me move that. Your request is for 38,040 times 128 hours. That's right, isn't it? Putting your request orders of magnitude above what we would normally allocate. What I think I will do is give you 1,000 node hours a month, but then you overdraw your account by as much time as you can get. Let's see. The deal, though, is that we'll put your jobs at a lower priority in the queue so that the code developers and debuggers get first shot. And flipping between Zoom and Keynote. I'd like to see you get your work done, so I'll try to accommodate you if at all possible. On the other hand, I don't want the other users getting upset with me. My sense is that a few projects are starting to show signs of life, so I hope you can get a lot of time now while the getting is still good. We still try and operate along that principle. And then he said, please write a nice paper for our year-end report. You're one of the few true production users, and I need someone to say this was worth the effort. Well, I actually looked at the NERSC annual report starting back in 1997, and let me just say, we did try to write, and I think we did write a bunch of nice papers over the years, but they weren't always right at the end. Sometimes these papers take years to produce, and my final comment is, some things just haven't changed over the years. We always want more time. So again, for ancient history, I have something about systems I've used at NERSC. So on my desktop, because I have different usernames at different places, I usually make an alias for every computer I want to log into. And so I just had to say alias grep NERSC, and I found all these different computers I've logged into in alphabetical order. And NERSC has a web page where you can find a list of the systems. So there was this one system, H4P, and there was an alias that actually used Telnet. So this absolutely has to be the first system. Everything else uses SSH. Probably most of you don't remember Telnet. And I think that this was how I accessed H4P, the Cray T3D, which on the NERSC list of systems since '74 is listed for 1994, but doesn't have a name.
Right.
And then in '96, we went to Franklin, Cray YMP, '97, MCurie. And, I don't think I need to go through this list in great detail. But I have said something about how the chips have changed over the years. For instance, Hopper was a quad-core Opteron. Nehalem was also quad-core. Edison had 12 cores and dual socket. And this plays into a little bit of what I was talking about later. And finally, we have Perlmutter, which a GPU machine. So without spending too much more time on that, let me go back to this slide on fun facts. So Richard mentioned this list of top users over the years, and he sent it to me months ago, and I've noticed that my friend and retired collaborator, Doug Toussaint, he's #1 on Richard's list of all-time users, and this is in NERSC days and NERSC hours. So this is equivalent, according to what Richard told me, of taking whatever the machine is at NERSC in any given year and seeing what fraction of the person used of that whole machine. And that's, if you used 1/365, that's one NERSC day. And so this is what Richard has found. And he also uses the top user for every year. And, you know, it shows what a slacker I am compared to Doug. He's been running so many more jobs at NERSC. And then going down a little, we have Don Sinclair, another Lattice. We have a couple of Lattice QCD people. And then we have my colleague Carlton Tatar, who's on this call today. And then at the bottom, we have a few more Lattice people. So 7 of the top 10 are Lattice QCD. And now I'd like to turn a little bit to the physics picture, since it's not just about computing. So from the mid-1980s to the mid-1990s, we were doing calculations with 2 flavors, just the up and down, the 2 lightest quarks. And we were using what's called naive, staggered, or Kogut-Susskind quarks. And in this formulation, we could not make the quarks light enough to get, you know, good values for physical quark masses, but we could extrapolate, and that we had to extrapolate. Starting in the late 1990s, we started using improved actions. And these are more complicated, so they make the coding tougher, but they have, and you know, there's more flops involved for any given lattice spacing. But just like using, you know, Runge-Kutta 4 lets you use a bigger lattice spacing and get a good result, using improved actions lets you use larger lattice spacings and get more accurate results. And there we added a strange quark mass. So there's a paper in Reviews of Modern Physics summarizing the whole program we did with this action called the ASCTAD action, which stands for A squared improved, tadpole improved. And then our 3rd generation of calculations used what's called the highly improved staggered quark action, also called HISC, and we've added a charm quark. So most of the work done in this series of calculations is done in collaboration with the Fermilab Lattice Collaboration, and some of it is done with the High Precision QCD Collaboration, who are the inventors of the HISC action. And now we can run with the light quark mass at its physical value, which I showed in that colorful slide with the circles. And so I'm going to have another slide about generating an ensemble at almost the finest lattice spacing we've used so far. It's the finest lattice spacing we've used with a physically light quark. And I must say, we're looking forward to NERSC 10 for reducing the lattice spacing from 0.042 Fermis to hopefully 0.03 Fermis. And what are the physics goals? Well, it's not just to create the ensembles, it's to determine something about nature. So we'd like to calculate the quark masses in nature because quarks are in bound states, the experimentalists can't just weigh the bound states because there's all this gluonic energy. And the question is, how heavy are the actual quarks? We like to study weak decays of heavy quarks to determine what's called the Kobayashi-Muskawa mixing matrix. And let me point out that Kobayashi and Muskawa got the Nobel Prize for defining the 3x3 mixing matrix. But we have to figure out what the values are in the matrix. And I'm not sure there's going to be a Nobel Prize for that. At any rate, another very interesting thing to calculate is the hadronic vacuum polarization contribution to what's called the muon anomalous magnetic moment. And I'll have a couple slides about that later. And then we've also studied QCD at non-zero temperature, which is related to the quark-gluon plasma, which has been studied at Brookhaven National Lab in the Heavy Ion Collider. So bullets 2 and 3 represent the search for beyond the standard model physics, which is very exciting if we can find evidence for that. So let me show you a few slides. These are from papers that actually I made sure they acknowledge NERSC, which is good. So this one is from 2018, which is a paper on the quark masses. And the plot here shows the ratio of the strange quark mass to the light quark mass. So I said the light quarks up and down are quite a bit lighter than the strange. The ratio is about 27. And what you see is at the top of this is our calculation in 2018. And then there's a gray band showing how our very precise result compares with other calculations. The top three calculations use up, down, strange, and charm in the C. So ETM with those big errors off to the left a bit uses twisted mass. And that was, 4 years before our calculation. But if you look at the other calculation just below that, Fermilab MILC, the same year is our calculation using staggered quarks. And then below that are three results on where from the earlier calculations, ASTED in our case, with only up, down, and strange in the C. And you can see the earliest graph or earliest plot here point here is from MILC in 2009, and it's comparable to the other calculations with up, down, and strange. And then you can see another twisted mass calculation that only has the two light quarks. So that's that, and I think you can see how precise we have done. Oh, and by this paper had 295 citations as of yesterday or so. I really like this next plot because it's very pretty and it shows what happens with very heavy quarks, which are tough to put on the lattice. So the thing about lattice calculations, you should have the lattice spacing times the mass of a particle to be a small number. And if you're looking at a particle with a very heavy mass for a given A times M is a large number. And so what we're doing on the left hand, on the horizontal axis, we're increasing the mass of a heavy quark. And over at the left, you'll see a vertical line marked with a D. That corresponds to the charm quark. And what was really challenging was making a heavy quark as heavy as the one in the B meson. And you see a vertical line with letter B. And what you see is a series of curves for three different lattice spacings. And you can see, I guess it's a cyan marked continuum. And you can see each one of these curves pulls away from the continuum. And that's because at that lattice spacing, as the quark gets heavier, there are effects that are proportional to A times M. And as A times M gets bigger, those systematic errors get bigger. And so you peel away from the continuum value. And you can see with these three different lattice spacings, we had three different cases, each of which, as we go to finer lattice spacing, more closely follows our continuum fit. And what you can also see, I hope, is that some of the points that actually are gone through pretty well are open. They were not part of the fit. But so the fit goes only up to these dashed lines in each case. There's a dashed line for each lattice spacing. So this was very nice. And this is how we determine the decay constants that I show on this slide. So in this case, you can see again, our decay constant has way smaller errors than all the other cases. I guess in the interest of time, I'm not going to go into the details of each one of these things. I'd like to switch to the muon anomalous magnetic moment. So this is a very interesting thing that we're studying on Perlmutter and other places. So an experiment E821 was done at Brookhaven 20 years ago. It's one of the most precisely measured quantities in all of physics, the magnetic moment of the muon. It's a brilliant experiment. But it turns out the result from that experiment was about 3 or 3.5 standard deviations different from the theory at the time and the theory as it's developed over the years. So the superconducting magnet from this experiment was moved from Brookhaven. It was shipped around Florida up the Mississippi River on a barge, and they mounted a new experiment, E989 at Fermilab. Again, spectacular experiment, except for the magnet, all the other instrumentation is new. They had spectacular agreement with the Brookhaven result, so it's not like Brookhaven made an error in the experiment, and that explains, why the difference between theory and experiment. And of course, finding a difference between theory and experiment would be evidence in new physics. But 3.5 standard deviations is not enough to claim that. 5 is our criteria for saying there's evidence for new physics. So Fermilab is going to announce their final results in a couple of months. So what has happened? Well, in the meantime, there's two theoretical results, and they're not in great agreement now. For a number of years, the lattice QCD calculations just were not precise enough as the other approach. And I give a colloquium about this where I call it muon G-2, more plot twists than a Hollywood movie. So we're right now in a plot twist time, and it seems like lattice QCD is the leading theoretical approach because some of the experimental inputs to the other way of doing things have changed, have been updated. So it's an interesting time in far that. So this is our results in red for what's called the windowed quantity. It's something that many groups can calculate. And what you can see is in the upper left-hand panel, which is the biggest part, our error bar is comparable to the best calculations. So we're doing very well there, and several different groups are in good agreement. If you look at the upper right, the errors are pretty big, but if you look at the horizontal axis, you can see that this is a very tiny contribution. This is less than 1 unit compared to the 206 units on the left. So it looks like a big problem, but it's not really a big problem, but that our red error bar is not as small as we'd like, and we're plan to use time on Perlmutter to improve that in the next year. We have an air cap. And then in the other cases, this on the lower left is the contribution of the strange quark, which is smaller than the light quarks. And on the lower right is the contribution of the charm quark. And, there again, we're comparable to or better than most of the other calculations. Okay, I wanted to talk about Perlmutter. I said I would. So we've been using Perlmutter for generating what I said was our ensemble closest to the continuum limit with physically light quarks. And we actually started generating this in 2014, and it was half done. We wanted 1,000 configurations. It was half done in 2018. So at the time, it was very hard to do this. And we just stopped for 3 years and did measurements with the other ensembles we had and what we had of this kind of half as big ensemble as we'd really like. But then in 221, Perlmutter came on, and look at how steep that red curve is. So we really made a lot of progress on Perlmutter, and that was great. But then it turns out, remember, we had to get time while the getting was good. Well, after the early science time kind of ended, or all the users got on, we were getting less time. So you not only need a very powerful computer, you need to get the hours on it. And then I have some cross-platform comparisons. So we ran that ensemble on Edison, on Cori, on Blue Waters, and then we got to Perlmutter with Slingshot 10. And you can see I give in this plot how many MPI ranks we were using. So I think Edison was actually 768 nodes we were running on with 24 cores per node. And I think we were using hyperthreading there. And you can see it took about 7.5 hours or 7 1/3 hours. Cori, 5 hours. Blue Waters, almost 9 hours. And then we got to Perlmutter, and in 1.5 hours, we could get the same amount of work done. And then we actually weren't running this for a while, and then we started running it again once the Slingshot 11 was available, and that only takes about an hour now. So that's really very nice. And I ran the code on Aurora recently on 32 Aurora nodes, and that was 2.27 hours. So the next thing I want to talk about was comparative GPU performance. I realize it's kind of the end of my 30 minutes. So instead of going over the details, these slides will be available. I want to show you a plot. So this is GPU performance by changing the local volume, which is L to the fourth. It's a function of L, and it's megaflops per second because that's what our code is printed out from the days when computers were so much slower. So you see on the left-hand side, it's 10 to the sixth. That's 1 teraflop. And each of these GPUs reaches a teraflop on what you would normally run on one MPI rank. So for instance, on Aurora, there are 2 tiles per GPU, and on Frontier, there are 2 GCDs per GPU, whereas on A100 and Grace Hopper NVIDIA, there's 1 GPU. So it's not a node-to-node comparison. It's just what you can do with 1 MPI rank, no communication. And you can see how Grace Hopper, because of the high level of parallelism and huge memory, outperforms the others. And you can see a difference between the 2 types of nodes at on Perlmutter, the ones that have 80 gigabytes, which have a higher memory bandwidth than the ones with 40. And you can see some of the curves move out further to the right because they have more memory that you can exploit, you know. All right. I'm going to skip the next slide. I want to mention that we have a really great software development community, and we have 2 different ways of computing fast on the GPUs. One is called CUDA. It's a project that started at Boston University in 2008. 2 of the earlier developers are at NVIDIA now. A couple of our postdocs, one of mine and one from Boston University, also work for NVIDIA. Some of you may be aware that Balint Zhu, who worked at Jefferson Lab and Oak Ridge, now works for NVIDIA. One of the people I worked with for doing the initial CUDA coding for staggered, Guochun Shi, well, unfortunately, he went to work for Google, not for NVIDIA. So we miss his contributions, but we get great support from NVIDIA. And CUDA has been generalized so that it doesn't just support CUDA, CUDA. It supports HIP, SYCL, and even OpenMP. And then another thing we use is Grid, which is developed by Peter Boyle. And I have a few things here about some of the things we're doing to make use of eigenvalue deflation and multigrid. This is not all in Grid. Some of it is in Grid and some of it is in CUDA. And I have a couple of postdocs working on these things. In view of the time, I will go to my last slide. Since Richard asked me to say something about future needs. So we still love high memory bandwidth. It's very important, and we love GPUs. Now, in the past, I would have told you we don't care very much about I/O. But with all this deflation and having lots of eigenvectors around that are much bigger files, because we have so many eigenvectors that we use than the gauge configurations, we really care a lot more about I/O now. And NERSC has played an essential role in supporting Lattice QCD for multiple collaborations, and I expect it to do so in the future. And I look forward to continuing to compute at NERSC, but probably not for the next 50 years, unfortunately. Thanks again to Richard for inviting me to speak. And I'd like to thank all my Fermilab Lattice and MILC collaborators over many years. I hesitated to make a list out of fear that I would leave people out. And a final thought, we still have lots of jobs to run, so we all need to get back to work. Thank you for your attention.
All right, thank you, Steve. That was great. I think if you have time, we could take a few questions.
Whatever you like.
And I think in this connection, anybody can speak and ask questions if you'd like to. I'll start with one about your gauge configurations. How big in aggregate are they, and how do you share them? Are they public? Or do you have like a portal where people share them? And how does that all
Good question. Good question, Richard. So the total size, we don't keep very good track of. We probably should. but it's probably around 4 petabytes now. I should look again. It's like either 3 or 4 petabytes that we have on Ranch. So Ranch has, and we do have some of that 042 at NERSC. And NERSC was the home of what was called the gauge connection, which was once described as like one of the first web portals. And somehow it doesn't have the support either from the community right now or at NERSC, I think, to really make it the major portal like for the US. There's something called the International Lattice Data Grid, which has community grids in different countries to try and share configurations. So we don't really rely on the gauge connection. Fermilab has a mass storage system and disk. They have a lot of our configurations, but it's only easy to share within people that belong to US QCD because they can get accounts there. So I sometimes get requests from people outside the US. I've done it for people in India a couple times. And they say, we'd like your configurations. And I wound up telling them to make sure they have a Globus connection, and I, move things up to their disk capacity. So it would be nice to have another way of doing this. On the MILC webpage, a part of the wiki, there's a list of publicly available configurations. And we also, by agreement, make other configurations available to groups who do things that are complementing us, not trying to scoop us. So that, there are the public ones and the ones that are held back till we finish some papers. Did that answer all aspects of your question?
Yeah, I think that was great.
Thanks.
The Slingshot 11 data point was really interesting, so I might steal that slide from you at some point
Sure.
as well. I don't know, do we have any other questions? I had another one that slipped my mind, I think. Oh, and I looked up
hand up.
Oh, okay. Yeah, Brian.
Hi, Steve. You mentioned earlier on that you participated, like helped us NERSC prepare some benchmarks using MILC.
MILC and CUDA.
Yeah. And
Sorry.
I just wanted to, extend my thanks in working with me on that for this last go around. I thought you were really patient in dealing with a non-QCD expert, and I learned a lot in addition to getting a really useful benchmark out of it. My question though is about you mentioned some future work in which you would like to lower the error bounds on one of your calculations. And I was wondering if that reduction of error bounds was limited by sort of Monte Carlo statistics and would only go as 1 over root n, or if there's like a different part of the algorithm that governs it.
Well, let me kind of answer that in a general way. So usually in the paper, when we present the results, there's what we call an error budget. And part of the error budget is from statistics, and part of the error budget is from systematics. And the systematics are divided up into different things, different categories. And so if the category is the lattice spacing, the control of A goes to 0, then we'd probably like to add another lattice spacing to improve that. But in general, adding statistics always makes you sharpen up the systematics because you understand them better. So that's a pretty roundabout general answer. And you have to look at each calculation and see what's limiting. And right now for the muon anomalous magnetic moment, one of the biggest issues is setting the scale properly. Because that's an error of 1% in the scale would result in a 1.8% error in the anomalous magnetic moment contribution because of the way things are. It just gets blown up by a factor of 1.8. And so we are about to publish a paper where that error is 0.4%, if I remember correctly. It's either 0.4 or 0.46. And we would really like to get that down further because we'd like to have the whole calculation have an error of 0.5%. And so, that's part of it. So, we're going to see if we can make this ensemble at 0.03 Fermis. I'm actually doing a lot of studies there to see what kind of parameters we can get away with to create that ensemble. And that ensemble will be on 196 cubed by 384. It's considerably bigger than the 144 by 288 that we're running now on Perlmutter. And, it'll need smaller step size and things, lighter quark masses. And I'm running tests on 96 to the fourth to see how our algorithms work on that. I hope that answers your question at least a little bit.
And I think it did. Yeah, thank you.
And thank you. It was a pleasure working with you on NERSC benchmarks. And when I actually downloaded them from NERSC, it was nice, very nicely organized.
Great, thank you.
Sure.
Thanks. Well, should probably let people go, but I can't end without asking you to at least make some comment on AI because you gave a whole talk. I don't think mentioned it.
AI. Well, there are people using machine learning to try and generate configurations, but as far as I can tell, they haven't put me out of business. So if they can do it, great. I'll learn what they've learned, but haven't seen that quite. There are things I like about AI, like I wanted every so often I ask ChatGPT to write a program for me because it can do it a lot faster than I can. And you also didn't ask me about quantum computing. And so I'll tell one of my standard comments is I achieved one of my career goals. I retired before I needed to learn about quantum computing.
Good. Okay, well, I want to thank you again, Steve.
Pleasure.
Great talk. And if you could send me your slides, that would be great.
I'll happy to do that. You want is PDF fine?
That's great.
Okay, thank you.
All
Thanks,
right,
everybody.
thank you, everybody. Bye.